I want to recap and make a little more precise maybe what we were saying in class about areas, velocities, and the fundamental theorem of calculus, and make sure we understand some notation along the way perhaps. The problem I'm going to look at is to find the area under y equals 1 over 1 plus x squared from x equals 0 to x equals 1. Let's get a sketch graph of that. This is an even function because x only appears as a square, so it's symmetric about the y-axis. The biggest it ever gets is when x is 0, and that's when y equals 1. And then it goes down and gets smaller and smaller as x increases, and gets as small as you want. It has a horizontal asymptote of 0 as x goes to infinity. So it's a hump shape, basically. So we'd like to find the area of this little bit in between 0 and 1. And I want to discuss various approaches, starting with low-tech and ending with very slick, namely the fundamental theorem of calculus. So I'm going to delete that to have some more space. And let's look at the low-tech approach. So here is just a part of that curve from 0 to 1, kind of rescaled. So here's that hump, and then it comes down, gradually comes down to 0.5 by the time x equals 1. And so I've put some rectangles under here to indicate the idea of using the rectangle method here. So if that's our problem, then if we want an approximate answer, we could use a variation of the rectangle method. So for example, we could use right endpoint method with n equals 5. Put that in math mode in case I need it. And that's what I'm illustrating here, that I divide up the interval into 5 segments, equal segments. Doesn't have to be equal, but it's much simpler to write down a formula for if it's equal. All of delta x equals 1/5. Match up the right endpoint, find the function value at the right endpoint, so you get the top right corner of the rectangle, and draw a rectangle of that size. Now, you don't absolutely have to draw the picture and draw the rectangles. You do that when you first get the idea, but algebraically, it's going to be something we can write down just with formulas. So remember, delta x is b minus a over n, always. Here, that's just 1 minus 0 over 5 is 1/5, and that's why those widths are 1/5. Okay, and so the right endpoint method for n equals 5 says that the area is approximately going to be equal to that delta x, well, let's write the general formula, times a sum of the function values, because it's sum of height times width. And if we want names for those guys, let me put a general parentheses around this. Okay. Then that would be x1, x2. Something's going wrong here. Okay. Yeah, that's what's going wrong. So f of x1, f of x2, plus f of x3, plus, I keep going past the plus, that's what's going on, f of x4, plus f of x5. Okay. So that's going to be a general formula where x1 through x5 are the right endpoints of the first, second, third, fourth, fifth rectangles. If we want to talk about the left endpoint of the left rectangle, a handy name for that one is x sub 0. And that fits into the numbering pattern much better. So that's a natural place. If we want to call this x1, well, what should that be? Oh, it should be x0. Okay, so we sometimes use that when we use the left endpoint, or say the trapezoid method, which refers to that as well. Okay, so that's approximately equal to 1/5 times, and then I just have to plug in all those values. Well, this is where it gets tedious, as anyone who's done this a little agrees. Okay, this is tedious enough. Oops, that's 0.4 squared. We've got to figure out what those endpoints are. Well, it's 0.2, 0.4, etc. Oh my goodness. And this is just for n equals 5. Squared plus 1 over 1 plus, well, this one's simple, 1 plus 1 squared. Okay. Goodness. Well, let's see what that actually gives us. Let's use the power of the computer here. Okay, so about 0.73373. Okay. So, where do we go from here? From that approximation to the area, we could just make delta n larger, therefore delta x smaller, and the number of terms here bigger, and just do it out by hand. That would not be fun. We could try a different method, like using midpoints or trapezoids, and I think I'll save that for another video. We could systematize this a bit better, and that's something we're going to talk about, and talk about summations. So what we would do is write that using the summation notation, which we're going to have to review just a little bit. There, the area is approximately going to be, this is delta x still, assuming we're using the same size in subintervals all across, times the summation, let's say k equals 1 to n of f of xk. That's at least writing it a little nicer. Or in this case, that's going to be 1 over n times the summation k equals 1 to n of 1 over 1 plus xk squared. Can we be a little bit more explicit? Well, yes, we can. So this is just taking this idea of a sum of a pattern, turning it into the summation symbol. We saw that it's 1 over 1 plus all these xk's squared. Okay. And then we just need to be more explicit about what the pattern of the xk's was. Let's put that in. Let's squeeze that in up here. X sub k. Well, the first one was we start at 0 and we go up by delta x. And then we go up by delta x again, and then we go up by delta x again, and then we go up by delta x again. Okay, for this case, it looks like it's 0, because that's your starting point, plus, k delta x. In general, for the right endpoint method, the kth right-hand end of the kth subinterval is going to be start at a, and then go k steps of delta x. Or if you like it all in terms of a, b, and n, k times b minus a over n. In here, in this example, we know delta x is just 1 over n, and so it's going to be particularly simple, k over n. Okay, so we could actually put in a k over n squared. Okay, well that's nicer. It looks nicer. It looks tidier. It's fewer symbols. Even though it's for a general n, it's fewer symbols than this whole thing that fits across the width of the page. But it's still a lot of work to calculate. We could grind this out on the calculator. We could program the calculator, use some sort of summation command on the calculator to get this. But it's still disappointing because it's still just an approximation. Okay, so to continue this style, we would need to take the limit. And the problem is that for most kinds of expressions like this, including this one, we haven't the foggiest idea how to actually find that limit exactly. We would actually have to make a table for various different n's, 10, 100, 1,000, a million, whatever, and kind of have to guess the limit. That doesn't prevent us from writing down a formal symbol for the answer, which is the limit as n goes to infinity of all these different guys. And we'll play this with this a little bit, but I really want to de-emphasize the symbol pushing aspect here. That we're going to have summation, and then that's going to be a rectangle method for a particular choice of how many n's there are. And then we compare for a bunch of different n's and we try to take the limit. I don't want to say that this is useless. There's a lot of good in here, but I do want to illustrate the value of the shortcut provided by the fundamental theorem. Okay, so we've had this problem. We had kind of a brute force attack on it, and brute force knowing some ideas about calculus, like summations and limits and things like that. But here's the indirect attack that we discovered in the last couple days. we're going to first convert it to a velocity distance problem. And second, we're going to solve that velocity distance problem by anti-differentiating. So the first observation is that if this horizontal axis is time and the vertical axis is velocity, then we can summarize, we can say what's been done here. Instead of talking about this calculation with the summations or even just the lower tech version with the 5 things as an area calculation, we can say, if this is 1/5 of a second, if that's a delta t, and this is a velocity figure, so that, remember, was the height of this guy. So that's the velocity. If this is the velocity as a function of time, and so here's the velocity at 0.2 seconds. I'm going to use that as a rough and ready representative of the velocity over all this time. It's not terribly accurate, but we know it's an approximation. And we're going to take that velocity figure, which is the height of this rectangle, times the width of the rectangle, which is how much time that velocity seemed to be active, roughly. Well, there's 2 interpretations for that. Width times height is area. That's the interpretation here. Or time times rate is distance, or time times velocity is the distance. And so the area of this rectangle is roughly how far that particle went in the first 0.2 seconds. And the area of this rectangle is roughly how far the particle went in this 0.2 seconds, and so on. And so this calculation, which seemed to be this 0.733, which seemed to have only one meaning as the approximate area under the curve, it's also approximately equal to the displacement. How far from whatever starting point you had, let me non-math mode that, displacement of this particle from time 0 to time 1 if the velocity is given by f of x. If f is the velocity. Okay, so the translation here in step 1 is that y equals f of x, that gets turned into v equals f of t. Just changing letters, that doesn't do anything. And interpreting the vertical coordinate as a velocity and the horizontal coordinate as time. And then area gets turned into the displacement. And it just comes from the fact that area equals height times width is exactly analogous to displacement equals velocity times time. Okay, so that means that any area problem we can, if we want to, convert it to a velocity distance problem. Why on earth is that useful? It's because we already know how to solve velocity distance problems. We know a totally different relationship, well, not totally different, but a different way to say this, that displacement is velocity times time. For a long time now, we know that velocity is equal to the derivative of position. And so we can get position information, which will get us the displacement, because that's after all just a difference in positions, by anti-differentiating a velocity. Okay, so how's that going to work here? We've got our function, so I'm just going to rewrite this with the function here, let me copy it, as v equals 1 over 1 plus t squared. And then we're going to have s of t, so that's v of t, is the antiderivative of that function. Now here's a notation. It's a sort of stretched out s, the antiderivative of 1 over 1 plus t squared. And then we put a strange thing. We put a dt. Remember that differential? The differential notation? we put those in here, and we'll talk about exactly why we do that. I'm going to put a little space to make it prettier. And this is called an indefinite integral. And it's just a notation for an antiderivative that it's going to match up with notations for area problems and the other strategy, the rectangle method strategy. Okay, so that's going to be, well, gosh, what is that function? Now here's where I picked one that's purposely weird. This is one where you don't want to try and start just do this with algebra, because you're not going to get anywhere. You have to look at your derivative table and say, ooh, have I ever seen anything whose derivative is 1 over 1 plus t squared? And strangely enough, it is the inverse tangent function of t that works. Now, if I wanted to get just a general antiderivative, we'd have to add a constant. But here's where a nice little trick happens, or a nice little simplification happens. The only thing we're interested in is the displacement. That is equal to the difference of the position at 1 and the position at 0. So it doesn't really matter what I pick for this constant. It's going to cancel out when I subtract. And so in fact, we're actually not even going to worry about that. We're not going to write it in twice and then just have it cancel. We're going to just take that s of t function and we're going to evaluate it at the 2 points and then subtract. And there's a notation for that as well. If you've already started using this notation, as we will soon, for the antiderivative, what we do is we decorate that with these little 0 and 1. That's analogous to the lower and upper limits for a summation. And the stretched out s that makes the integral sign is actually a very stylized version of a sigma for sum. And so this is a notation that means take the antiderivative of what's inside, which we happen to know is inverse tangent of t, which is a cool and weird fact, and evaluate it at the top and at the bottom. There's even another notation for that to emphasize the two-stage process here, and that is put it in brackets, or sometimes we use just a vertical line for that. And we'll explore the various different notations for that. It says take this function, which is the antiderivative, plug in 1, plug in 0, and subtract. So that's just a simple notation for this guy. And I happen to pick one where we can do it by hand. The inverse tangent of 1 is the angle, the mystery angle, of course in radians, whose slope is 1. And that is pi over 4. And this is the mystery angle whose slope is 0, and that's 0. So it turns out the answer is pi over 4. That would have been really, really hard to get by the limit of a sum. Even if we were really good guessers, it would have been really, really hard to figure out that that was the answer. And this fact that this pi comes in, you'd never guess that. If you say, look at this, what are we doing here? We're doing like a 1 over n, we're taking these algebra stuff, just algebra arithmetic. It's a pain, it's a lot of work, but why the heck am I going to get pi out of that? Well, look at this, 0.73, or 733, pi over 4, if I evaluate it numerically, it's in the right ballpark. And it's bigger, which makes sense because we knew we were getting an underestimate from that n equals 5 calculation. So, let's summarize. I know this is a long video, but I want to summarize here. We didn't really have to think of it this way. I wanted to think of it this way because it makes it more obvious that we actually know the answer to this problem already, because we've done anti-differentiation to solve velocity distance, and we know that also has something to do with the area problem. But we didn't really have to change the letters to v and t. That's really all it amounted to. So what we could do is we could just say y equals 1 over 1 plus x squared, and we want the area from 0 to 1 under the graph of 1 over 1 plus x squared. That's a notation for that area. Okay. And all we have to do is to say, okay, we've got a strategy for that. We interpret this as an instruction not to calculate area by rectangles, but to take the antiderivative of that thing, which was inverse tangent of x, evaluate it from at 0 and 1 and take the difference, and that's what gave us pi over 4. And so this symbol really can be interpreted in two different ways. It can be interpreted as we want the area and we'd like to use the rectangle method, but no thanks, it's too hard. Or we can interpret it as instructions to take the antiderivative, which was what the symbol would mean without the 0 and 1, and then evaluate it at 1 and 0 and take the difference. And so the upshot is that the area under any curve y equals f of x, and we're going to have to modify this a little bit, is, well, let's see. If that's little f, we have a standard name for how to go from little f to big F. We call this thing big F. Big F, under f of x from x equals a to x equals b is f of b, minus f of a, where f is any derivative, antiderivative of little f. Comes out weird in the display font, but so that's going to be one strategy for finding the area, and that's one version of the fundamental theorem of calculus. We take the antiderivative, any antiderivative, don't worry about the plus c. We take the difference of those two values, and that's going to calculate the area from x equals a to x equals b.